In the meantime, can you start to share the screen and see if everything is working?
Oh, of course. Okay. So do you see my screen now?
Yes, it works.
Okay, so let me hide the all right.
Okay, yes, I can see the screen.
Oh, perfect. Perfect.
Okay, so let's wait for 1 minute and then we can begin.
Sounds perfect.
Okay, welcome everybody to this week's Majorana-Raychaudhuri seminar series. And today's first speaker is Valerio de Luca from University of Pennsylvania. And he's going to talk about superfluid dark matter from theory to of observation. And maybe I can send you a reminder when 5 minutes are left.
All right. Many thanks, Anish, for a nice introduction and for the kind opportunity to give this talk. It's a pleasure to participate to this interesting seminar series. Yeah, so today I will discuss about superfluid dark matter, providing some theoretical backgrounds of this model, and then discussing prospective probes for observations. But let me start by reviewing briefly the dark matter problem. So as you know very well, dark matter is believed to comprise about 80% of the total matter content in the universe today, and even a larger fraction back at recombination and so on. And we got different evidences on the existence of dark matter from independent observations.
I'm just listening to the...
which include galaxy rotation curves, which were shown to be displaced from the baryonic prediction when only luminous components were taken into account, from CMB anisotropies, where the location and size of the peaks were giving information on the dark matter abundance in the universe, and also for large-scale structure, where dark matter is believed to provide the seeds for the structures to grow. Now, thanks to this observation, we managed to build up the cold dark matter model, in which dark matter is a non-relativistic particle at recombination. It is dark, so neutral under electromagnetic interactions. It has to be stable, and at least it is characterized by gravitational interaction through which these observations were made. But one may wonder what happens if we can go just beyond gravity. And an important observation comes from the Ballet cluster, where describing the collisions of two galaxy clusters whose center of mass was actually shown to be displaced from the baryonic-only component. So if dark matter have, let's say, further interactions, they have to be constrained, and indeed people managed to derive a bound on the dark matter cross-section, sigma, to be smaller than centimeter square over gram times the dark matter mass. Now, while cold dark matter performs very well on large scales, when you go on smaller scales, such as scale of galaxies, there are more uncertainties in the physics. And during many years, people have developed various problems, which some of them are now resolved. And this, for example, includes the CASP core problem, missing satellites, the too big to fail, and so on. Now, it is still unclear for some of these problems what is the role of baryons in helping cold dark matter to address these discrepancies. But I believe it is still important and worth to go beyond the cold dark matter to see if there are other models which may perform, let's say, slightly better on smaller scales. So I will use this as motivation to show that, in principle, people developed a lot of plethora of dark matter models, as you can see from this plot, spanning a big range in the dark matter mass. For example, around the GeV, people develop the weakly interacting massive particles, or WIMPs. But if you go, let's say, to heavier dark matter masses, you may have composite dark matter, primordial black holes even, while on the left there are ultralight dark matter candidates, which are mostly bosons with mass below the electron volt. And the model of superfluid dark matter actually lies within this category, which is the one I will mostly focus on today. Now, in short, this model is based on the existence of bosonic particles with a mass below the electron volt, which are characterized by repulsive self-interactions, thanks to which they can achieve a superfluid state in environments which are sufficiently dense and at low temperatures, such as the center of galaxies, through condensation. So within this talk, I will try to provide the background of this model and potentially prospects for observations. So this was a sort of brief motivation to the talk, and it will be divided into two main parts. The first part will be a part of model building, so building up the details of the model to see how we can realize the superfluids in galaxies. And then in the second part, again, I will try to provide a few phenomenological implications for this model. And the results I'm going to show today are actually based on a review we are finishing for Physics Report with Lascian Bereziani, Giordano Cintia, and Justin Curie, which is supposed to be published in a month or so at most. Okay, so if there are no questions on the motivation, let me start by discussing the model building. And let's go back to the notion of superfluids. So the first fluid which was discovered to have a superfluid phase was actually liquid helium more than 100 years ago. And it was actually understood how superfluidity is an effect, is a quantum effect, which happens to be relevant when you go at very low temperatures. So since the discovery, Landau managed to provide a better understanding of how superfluidity is achieved for fluids in general. So it was understood that this is a property of fluids when they are cooled below a certain critical temperature, which will depend on each fluid. And it has the nice property that it can flow, so it can transport charges, such as helium atoms, without friction. Now, to understand a criteria which Landau developed, we can study the following. So, as you know, when we study fluids, the low energy degrees of freedom of fluids are actually phonons, which in principle can lead to dissipation. So when we consider a fluid moving in a certain capillary with a certain velocity Vs, then in order for the fluid not to lose energy through dissipation, the velocity of the fluid has to be smaller than the sound speed Cs of the fluid associated to the dispersion relation omega of the phonons, which will depend on the underlying microscopic theory of the fluid under consideration. So basically, the property of being subsonic was one of the conditions Landau developed for to achieve superfluidity. Now, since then, there was a better understanding of superfluidity through a quantum field theory description, for which superfluidity is actually associated to Bose-Einstein condensation. So the main idea is that a superfluid can be described as a configuration of bosons at finite density, which break spontaneously a global, for example, U1 symmetry. And in the talk, I will refer to a model of a complex scalar field phi, which has repulsive quartic interactions as a proxy to study what are the properties of superfluids. So in this theory, lambda is a parameter which is taken to be positive to allow for repulsive interactions. Now, under Bose-Einstein condensation, so when there is a classical field configuration, phi naught, which breaks the U1 symmetry, this property of superfluidity can eventually appear. And in this classical background, we can introduce the chemical potential, which is going to depend on the strength of the self-interactions of the theory you are considering. Now, whenever you break the symmetry, of course, there will be some non-Bose-Einstein bosons associated to the broken U1 symmetry. And those are exactly the phonons we are going to talk about. So in particular, we can study the properties of these phonons by perturbing around the homogeneous condensate, which has broken the U1 symmetry. So we can introduce H, a radial perturbation, and pi, which will be the phonons, so the angular perturbation. And if you go in the non-relativistic limit and by integrating out H, you can derive an effective field theory of phonons, which usually is written as a form of a P of X theory, where X depends on the phonons pi and on the chemical potential mu. Now, this will be, of course, model dependent. So in the case of quartic interactions, like we did before, you can see that you can derive, first of all, the equation of state, which characterizes this fluid at zero temperature, where the pressure is proportional to the density square of the fluid, and the corresponding sound speed will depend on the quartic coefficient lambda. Similarly, you can also derive the dispersion relation for the phonons, which in general will pick up two different contributions. One, which is proportional to the sound speed that describes the strength of the self-interactions in the fluid you are studying. And then there will be a quantum pressure term, which is quartic in the momenta, that describes the relevance of quantum pressure. Okay, and I will go back to this relation in a few slides. Now, let me stress that this kind of picture can also be understood through an hydrodynamical formulation. So in particular, in this limit, a system of bosons can be described through a wave function psi that satisfies the Gross-Pitaevsky equation shown in this red box, where now, aside from the quartic coupling, I also added a gravitational interaction to some external potential phi n for the relevance of galaxies and so on. Now, if you perform a Madden decomposition so that the function psi is expressed in terms of a density profile rho and a phase, which is used to build up the velocity through which the fluid moves, then we can derive the hydrodynamical equations, so the continuity equation for the density and an equation for the velocity, which now will contain the information of the classical pressure, so the sound speed, as in the dispersion relation, the quantum pressure term, similar to the dispersion, and eventually a correction, which will come when gravity is present in the system, such as in galaxies. So this can bring us to study a bit better the property of the phonon dispersion relation. In particular, when gravity is present, the relation is going to be affected by a contribution which is proportional to the density rho of the, let's say, of the fluid under consideration, and which in principle may induce Jeans instability, similar to what happens when you study large-scale structures. So all modes which are softer than the Jeans scale may actually be unstable. And we can introduce an effective coupling psi, which depends on the strength of the self-interactions, so that the two different regimes will be highlighted. In a regime where psi is much smaller than unity, so when, if you want, there are very low self-interactions, the Jeans scale is given mostly by the mass and density of the environment, and basically this is the regime where the quantum pressure term, k to the fourth, dominates the dispersion relation, which is the quantum pressure regime that is relevant for the model of fuzzy dark matter. So when we are basically in the very low end of the ultralight dark matter regime with masses around 10 to minus 21 electron volt. On the other hand, when psi is very large, so when there are sizable self-interactions, the Jeans scale will be dependent on the sound speed and on the density of the environment. So this case is the case of the interaction pressure, which is the relevant one for the model of superfluid dark matter. And it basically relates the sound speed term to be the most dominant contribution in the dispersion relation. So for today's talk, I would like to stress that indeed this is the kind of regime we want to consider so far. Okay. Now, given this background, we can already understand how can we achieve a superfluid state in galaxies. And the main conditions for this superfluid soliton to be realized in galaxies with a size given by the size of a galaxy, so let's say the kiloparsec, is through two different conditions, which are, again, Bose-Einstein condensation and thermalization. So let me start with the former. Now, the condition of condensation, if you want, is a condition of degeneracy, which basically demands that the de Broglie volume of the system is highly occupied, which means that the degeneracy factor n that tracks the occupation number, given by the product of the density of the environment and the de Broglie volume, has to be much larger than unity. Now, this condition will be satisfied until a certain radius, which we call the R degeneracy, and demanding that this radius is larger than the virial radius of the halo, this can allow us to have an halo which is completely degenerate. So for Milky Way-like halos, this condition can be rewritten as a bound on the dark matter mass to be, let's say, below the electron volt for characteristic dark matter halos. Okay, so this is one of the conditions we need to impose to have a degenerate halo. Now, under this condition, of course, there will be a coherent scale in the system, which will be given by the de Broglie wavelength. Now, for fuzzy dark matter, for example, when you study masses of the order of 10 to the minus 21 electron volt, you can see that the de Broglie wavelength at the size of the virial radius is of the order of the kiloparsec. But if you do the same game for superfluid dark matter, as I will show later, whose masses are actually much heavier, so in the millielectron volt, in the microelectron volt, you will see that the corresponding de Broglie wavelength is actually much smaller than the kiloparsec. So from this kind of argument only, it seems hard to create a state, a coherent condensate, with a coherence scale given by a kiloparsec. So how can we do so? Thanks to thermalization. So thermalization basically means that the bosons, thanks to their self-interactions, are able to achieve a configuration of thermal equilibrium, so they reach the maximal entropy state, which of course puts a bound on the cross-section of the self-interactions of the dark matter particles compared to the density of the environment, the velocity, and so on. Now, in practice, the picture we expect is the following. There will be an orange region which describes the condition of degeneracy, okay, of before, and then within this region, there will be a thermal envelope given by radius RT, where this condition is satisfied. And inside the thermal envelope, therefore, both conditions are realized, and this is where we may expect a superfluid dark matter to be achieved. Okay. On larger scales, though, at a certain point, you are going to match back to NFW as you expect for cold dark matter. Now, the picture in thermal envelope, though, is a bit more complicated than this. And the reason is that since the thermal envelope is usually larger than the Jeans instability, what happens is that the thermal envelope is going to fragmentate. So it will build up various islands of superfluids with a size given by the Jeans scale and with a density more or less given by the local NFW density. Now, these islands are going to interact among themselves because of tidal interactions. And our expectation is that by tidal interacting, they are going to be destroyed, generating some streams of weakly interacting particles all around the thermal envelope, but in principle, a central core is expected to survive, again with a size given by the Jeans length, which depend on the microscopic properties of the model you are considering. So this is the picture we have for sulfuric dark matter, but with the simulations to completely validate it. Now let's study a bit better this central soliton. So by studying the hydrostatic equilibrium equation, we can derive the profile ρ of the soliton as a function of the radial distance, and employing the equation of state for the quartic interactions, then this equation will turn out to be a Lane-Emden equation with a profile which is basically a core, which then fades out at a distance given by the Jeans length, which is proportional to the mass of the dark matter particles and on the self-interactions. So there will be some sweet spot in order to achieve a size of a kiloparsec, which is what we expect for galaxies and so on. Okay, so all these arguments can allow us to bring up a parameter space for this model to work. So this is the plot which shows on the vertical axis the dark matter mass as a function of the cross-section of the system. And there are already various coil regions where the model is ruled out. So in the dark magenta region, the self-interactions are so large that there will be decay process, so the condensate is basically evaporating with time. The light magenta region, on the other hand, is ruled out because the condensate will be relativistic at matter radiation equality, which of course we know is against the principle of the cold dark matter and so on. Then there would be a pink band bounded by Baller cluster, and then a light green region where we are in the region dominated by quantum pressure. So we are outside of the regime of sulfuric dark matter. The white region instead is the one which is completely allowed so far for the model to be true. Okay. So in the following, we'll mostly focus on masses around the milli-electron volt and corresponding cross-sections in this plot. Okay, so let me pause here if there is any questions about the first part of the talk. Otherwise, I will move later to the second part.
Valerio, hi.
Hi, Luca, yes.
Thanks for the introduction so far for these first preliminary results. So there's a question that came to me which deals with timescales. Like, could it be possible that this stripping has already occurred and we don't have filaments anymore? We just have the central soliton. Do you expect these filaments to be hanging around still? Yeah, something.
That's a very
about the
good question.
timescale.
Yeah, that's a very good question. To be honest, I don't know. We need simulation to completely understand the complete dynamics of the process. So I agree with you that it's unclear to me if those filaments are going to be there or not. What I can tell you is that our understanding is that when these particles basically start to achieve the fluid phase transition, at that point, in principle, this is what we understand should happen. So there are going to be tidal interactions and so on. But I agree that it's unclear if there will be further evolution in the system after the initial stages, let's say. So yeah, it's a good question. I don't have an answer yet. But I believe that this can be answered only through simulations. It's very hard analytically to understand how this can, yeah. I'm sorry for that.
Do you also expect this to be like a recurrent process? Like you have more nucleation happening even now? Or,
Yeah, it could be. So the interesting property is that the condition of degeneracy is actually time independent. So when when you basically undergo the phase transition, this will happen right away. However, thermalization, I believe, is there will be some time dependence. So let's say the recursion of the process will depend mostly if it happens on thermalization. So yeah, but similar to the previous question, it's very hard to have a complete analytical understanding of this of this process.
yeah,
But in principle, I would say so. In principle, I think you can. In principle, you can have more, let's say, stages where first you achieve a superfluidity, then you break it a bit, then you achieve it again. It's a bit. It's not easy to understand Yeah, completely.
Yeah, I agree. Maybe at the galactic scale, where you
Mhm.
have a potential change by order one, but you don't expect drastic changes. Maybe
Right.
you can expect this cycle
Yes.
to occur more frequently. One last very short question is
Of course.
how general the overall picture is. Like you show now this mass versus sigma plot,
Yes.
like is which basically answers the question of how general this is. But is there anything that could make this picture deviate from what you're showing now? Or
Uh, yeah.
yeah, something along this
Yeah,
line.
I understand the question. So I would say maybe the main point is the cross sections. So of course it will depend on the kind of interactions you are taking into account. Of course, let's say this model was mostly aquatic interactions, but in principle you can even go to axic interactions. So in that case, of course, there will be some difference in the cross sections on, and therefore you may. This is why the parameter, this kind of regions can change depending on the strength of the interactions you consider and so on. If you want, so this is the main one of the main, let's say, hypotheses you can take into account is the value of the cross section, which would depend on the model you study. Yeah, I think this kind of band here was done mostly for a quartic, so it will change a bit when you study, for example, X6 or so on potentials.
Yeah. If you open to higher order terms, you could even
Exactly.
have like
Yeah, exactly.
non-gravitational solitons.
Yes, yes,
Uh,
yes.
I agree.
Yeah,
Okay,
exactly. Thank you. Thank you for the
thanks.
questions. Yes.
Yeah, thanks.
Okay, so at this point, let me provide so I will try to discuss three possible implications for this model. The first one will be regarding vortices. The second is the behavior of dark matter around black holes. And the third will be dynamical friction. So let's start with the first. And the main idea is that when you have these dark matter halos, which are basically undergoing the phase transition in superfluids, if there is some angular momentum going on in the halos, then in order for the moment to be conserved, to be retained in the environment, superfluids have to develop vortices. And the reason is that the rotational superfluid is actually unhomogeneous. So the only way to have an unvanishing vorticity is by considering these vortices, which are a configuration, let's say, three-dimensional lines located at certain, let's say, density and position, with a direction given by the direction of the angular momentum at the beginning of the transition. So we can study a bit better the properties of these vortices by perturbing the superfluid configuration. And you will see that the size of the vortex of the core will be proportional to the healing length of the system, which again depends on the mass and the sound speed of the system. So if you plug in some numbers, you will see that you may expect vortices with the size of the meter for microelectron volt masses, for example. Now, in order for such a vortice to be produced, you need dark matter halos, which are spinning fast enough, which means spinning faster than a critical value that depends on the halo size R and on the healing length of the system. So if this condition is met, then you expect the production of uniformly spaced vortices, so a sort of lattice like defined in simulations, and the production will be very, very large. So in particular, for kiloparsec size halos, you may expect about 10 to the 18, for example, vortices. So a very, very big number of vortices going around the superfluid core, as was also confirmed a few days ago in simulations by Brax and Balages. So the question is, how can we find these vortices, right? And one possibility is through gravitational lensing. So gravitational lensing basically consists in the magnification of the light coming from a star to the observer because of the presence of some small-scale structures in the line of sight among them. And in particular, when you have vortices, which are under dense fluctuations, there will be a flux demagnification. So in principle, this could be one of the observables to look at to identify the presence of vortices in your environment. However, this is harder to say than to do because vortices have a certain critical velocity as they move. So we will need some time-dependent observables that can track the location of the vortex as they move. So this is a bit harder than expected. Now, in general, one can also ask if vortices are stable. And in principle, if self-interactions are absent, people have shown through simulation that they can decay with time. However, the presence of self-interactions, like we have in our model, in principle may allow to have stable vortices. And also, if there is an underlying gravitational potential in the system, such as black holes, this also helps in the stability of the vortices. So this is one of the kind of prospects we may look at to try to find, to confirm this model or rule it out. Now, concerning black holes, this brings me to the second direction, which is to study how dark matter behaves around black holes. And as you know very well, supermassive black holes exist at the center of galaxies, and we already detected various of them through the Event Horizon Telescope. And in principle, an experiment like LISA is going to be able to test the merger of binaries involving supermassive black holes. Now, when you have a supermassive black hole at the center of the galaxy, it is going to modify the dark matter profile around it because of the gravitational potential. And this will create what are called dark matter spikes, so enhancement in the density profile induced by the gravitational potential of the system. Now, the corresponding spike will depend on the properties of the dark matter particles you consider. For example, for cold dark matter, Gondol-Silk found 25 years ago that the slope of the profile is about 9/4. So there is a dramatic increase in the profile for cold dark matter, with the slope which depends also on other phenomena like scattering of stars, dark matter annihilations, and so on. On the other hand, when you study, for example, self-interacting dark matter, where the cross-section depends on the velocity, you will see that the slope is actually affected by the self-interactions of the picture. So different models have different spikes. And the question I would like to answer is what happens, for example, for sulfide dark matter. So in order to understand what happens, we have to identify in the, let's say, in the spatial distribution, the region where the black hole is actually relevant, which we call the black hole sphere of influence. So this is the region within which the black hole gravitational potential is going to dominate over the one of the dark matter. And it depends on the mass of the black hole and on the density of the environment. So we will highlight three different regions in space, starting from the black hole. There will be an outer region at distances larger than the sphere of influence, RH, an intermediate region, and an inner region very, very close to the black hole. So let's start with the outer region. And here, as you can expect, since we are at distances larger than RH, the gravitational potential of the black hole is going to be basically irrelevant. So we expect to match the superfluid profile we found in the first part of the talk. But as we go to smaller distances, so we enter the intermediate region, now the black hole potential is going to be very relevant. So it will dominate the potential of the system. But eventually, it is not strong enough yet to modify the properties of the superfluid dark matter. So to solve for the profile, we can solve the hydrostatic equilibrium equation for ρ in the full GR picture. So studying, for example, as a proxy a Schwarzschild black hole background, and employing the equation of state for the superfluids. So we can solve for the profile, and the solution will be valid until we reach the inner region. so farther closer to the black hole. So at this point, the black hole potential is going to become so important, then the dark matter is losing the property of being degenerate, but it will still remain thermal. So in practice, you are changing the equation of state of your superfluid in a sort of ideal gas picture. And you will have to solve the same equation coupled to the heat equation for the temperature. Finally, when you are very, very close to the black holes, so at marginally bounded circular orbits located at twice the Schwarzschild radius, then accretion processes are going to become so important that in principle the dark matter is going to plunge around the black hole and the density profile is expected to drop. So putting all these ingredients together, this is the result. So the vertical axis shows the density profile of the dark matter as a function of the distance from the center. So here in the outer region, you expect to match the core. And as you can see, within the black hole sphere of influence, there is an enhancement in the density profile. So there are spikes which can increase by various orders of magnitude compared to the mean profile. In particular, the blue and the green line shows two different, let's say, model of superfluid dark matter with different self-interactions, which give rise to a, let's say, mild enhancement in the density profile. The brown shows the case of self-interacting dark matter, and the red line shows cold dark matter. So as you can see, there is a big hierarchy between cold dark matter and this self-interacting model. And the reason is that when you have model with self-interactions, there is basically a classical pressure term in the system given by the sound speed. And the sound speed, the self-interactions, basically compete with the gravitational strength of the black hole and give rise to a shallower growth of the profile compared to cold dark matter. So this is a very unique feature which depends on the model you study. And the question is, can we detect these spikes somehow? And the one possibility relies on the evolution of binaries. So we can study systems that are called extreme acceleration spirals. So these are binaries involving the central supermassive black holes and a small body, which we will call the perturber, which evolves around the central black hole. So this system is going to evolve by emitting gravitational waves, as we know, but during the spiral, so as the perturber moves through around the black hole, it will also move through the superfluid dark matter environment, and eventually it can probe the existence of a spike or in general of a superfluid profile. So this happens through a phenomenon which is called dynamical friction. This phenomenon basically is based on the fact that when a perturber moves in a cloud of particles, because of gravity, it is going to create something which is called a wake. So a perturbation in the density of the environment induced by the motion of the perturber through the fluid itself. And as you create this wake, this density perturbation, there will be a gravitational attraction between the wake and the particle itself, which is what is called dynamical friction. Now, this was studied by Chandrasekhar many years ago in the context of cold dark matter, and now I will try to outline its behavior for superfluids. So the picture in mind is the one in which we have a probe of mass mu moving in a circular orbit around a supermassive black hole through a uniform superfluid medium. And this is the expression for the force of the friction, which depends on the dispersion relation of the fluid under consideration, in this case, the superfluid dark matter. Now, the force depends on the Mach number, which is given by the ratio of the velocity of the probe compared to the sound speed. And as you expect, we are mostly in the subsonic regime, which is characteristic of superfluid dark matter. But in principle, we are breaking the assumption of uniformity because the presence of a supermassive black hole at the center is a source of inhomogeneity. However, if you study the radial growth of the profile, you will see that in practice this is very small. So in the force, you can just replace the uniform density for the superfluid environment with a spike profile. So the result of this analysis is the following. So this shows the force of dynamical friction as a function of the Mach number in both the radial direction in green and the tangential direction, since we are moving over a circular binary. Now, the radial force is vanishing in the subsonic regime and features some bumps, as you can see, in the supersonic regime. So these bumps are due when the perturber basically crosses the wake which lags behind it in the binary. On the other hand, the blue line shows the force in the tangential direction, which is characterized by the usual Coulomb log. And in the subsonic regime, which is the one of the main interest for us, you can approximate this force through the following analytical expression. So the force depends on the mass mu of the perturber, which is moving through the superfluid, on the velocity with which it moves, on the density of the environment, and on the Mach number itself. Now we can compare this force with the expression found by Chandrasekhar for cold dark matter, given by this equation here. And the ratios of these two forces is shown in this panel as a function of the radial distance from the center. So as you can see, the force for superfluid dark matter is always much, much smaller compared to the force induced by cold dark matter. And the main reason is, aside from the Mach number which suppresses the force, is mostly due to the density profile, being that the cold dark matter profile is enhanced much, much more compared to the model of superfluids, which give rise to a much smaller force for the latter. Okay, and this is what we expect, of course, because superfluids is a fluid which basically moves almost frictionless. So we also expect a probe moving inside it to experience, let's say, a weaker force. Now, the dynamical friction is very...
You have 5 minutes left.
Yes,
it's
yeah,
a
I almost done. Yeah, thank you. So we can study how dynamical friction is going to affect the evolution of the binary by studying its competition against the gravitational waves. So this plot shows on the vertical axis the ratio between the dynamical friction contribution in the energy power as a function of the emission of gravitational waves in terms of the frequency of the in-spiral. So when the frequency is very low, which means that when the binary is very, very wide, dynamical friction is the main driver of the evolution of the binary. But then as you go to larger frequencies, so when the binary is narrower, gravitational waves take the lead and they dominate the evolution of the binary system. Furthermore, as you can see, the expression of dynamical friction for cold dark matter in red is going to be much more important compared to the case of superfluid dark matter. So the question is, can we somehow detect these effects at experiments of gravitational waves? And a useful parameter for this prospect is called the gravitational dephasing. So this tells the change in the number of cycles the binary makes through the merger with and without dynamical friction. So if delta n that measures this dephasing is smaller than unity, in principle, you can see that the binary has changed the number of cycles and eventually measure dynamical friction. Now, this plot again shows this quantity as a function of the frequency. And as you can see, in the low frequency regime, the dephasing is important because dynamical friction is the main driver of the evolution. But in the large frequency regime, the dephasing goes back to unity because gravitational waves are the dominant effect. And in particular, LISA, which is mostly sensitive to this region, therefore will be unable to measure dynamical friction for superfluid dark matter for sure, and maybe there is some small prospect for cold dark matter. On the other hand, if we study pulsar timing array, which are probing smaller frequencies, in principle, there the dephasing could be very important, and therefore it can give an important contribution to the evolution. So this is something we are actually working on right now. Okay, so given the time, I can just give you the conclusions. So I hope I convinced you about the interest in studying superfluid dark matter as an interesting dark matter candidate based on self-interacting subelectron volt bosons, which can achieve a superfluid soliton at the center of galaxies. And this model is characterized by very unique phenomenologies, including vortices, spikes around black holes, and dynamical friction, thanks to which maybe we can try to probe this physics through gravitational waves. But there are many, many things to do, also following up on the questions of Luca before. So for example, understanding in more details the evolution of the early universe cosmology, how it proceeds, and eventually perform hydro simulations to see how structure formation will proceed, and finally perform an in-depth investigation of the viability of the model from various phenomenological bounds. So with this, I thank you for your time and very happy to answer any questions if there are.
If there are any questions from audience, please unmute your mic and you can ask.
Yes, one small curiosity. So,
Yes.
have you considered the impact of self-interaction among the dark matter?
What do you mean by the self-interaction of the dark
So,
matter?
so you know that there are like several motivations for having self-interacting dark matter,
Yes.
right? And
Yes.
so while doing this analysis, if you have self-interacting dark matter, or if you have just no self-interacting dark matter, did you consider if that could be some impactful effect?
So the problem is that if you neglect self-interactions,